Okay, so today mostly concentrated on we should say the regularity of math. Slightly misleading because what I'm going to prove is not a complete regularity, the intermediate state, and then perhaps tomorrow completely use this and prove the regularity of the optimal map. Okay, so let the title be as it is, but first I'm going to start before proving that. I'm going to prove a theorem which I finished last yesterday. It's, remember that last time we obtained the optimal map is given by x is plus gradient x star of gradient phi naught, right? So this is the optimal map we obtained last time, and here this phi naught is P naught C naught is optimal in D, right? And we also have this characterization that Px is the supremum of y in capital Y, Cxy minus Py minus Cx, right? So you here. Right? So this is the calculation. Okay. So let us for the moment concentrate on the quadratic constant minus y square, and let me simplify this expression a little bit. Okay, so this is supremum y capital Y is 0 y. This quantity becomes minus half x square, and then plus x dot y, and then minus half. Okay, so this is the quantity, and so here supremum is over y, and this term is independent of y. Okay, so I just can take outside the supremum and bring it to the left side. Okay, so z sin of x plus half x squared is equals to supremum. Let me rearrange little bit. Y is supremum over y, x minus y plus y minus half. Now, can you recognize this kind of identity? I mean, this kind of. So you see, these are all linear, right? Linear, and we are taking the supremum of linear functions, right? So this is convex. So if you have resemblance with the definition of h star, sort of, right? So x dot y minus sum, right? So that is clearly a convex function. Supremum of linear function. So this quantity is convex. Now let us go back to our original Tx. Here h. So here h of c is just not z square, right? So it's convex. So h star is also mod z square. So if I write down the optimal map, so this is x plus gradient of h dash. So this is gradient of phi naught, right? So gradient of h star c is beside h star c. This is the legendary transform. So the optimal map is this phi, and therefore which I can write gradient of half mod x square plus sin of x. This is a convex function, right? So the optimal map is given by the gradient of a convex function in this way. Okay? So this is what we actually proved last time, and which recovers Brenier's theorem. Okay, and last time I mentioned that the pi, optimal pi, from the Kontarovich problem. The Kontarovich problem is the cyclical momentum, right? In the sense that remember this identity xi dot yi minus yi plus 1 or any finite collection of such number is non-negative, right? And here xi, yi. So these are from the support of phi. And as a result, by converse of by Rockefeller's theorem, this pi is support of pi is concentrated on a graph of a convex function phi. Okay? The subdifferential of the graph of a convex function phi. Okay, so this is what we mentioned last time. Now I'm going to start from here and sort of reprove that this pi is actually given by a gradient of convex function. This pi is induced by a graph. Okay. All right. So see the starting point. So here I don't use any duality or anything. So all I need is that the support of pi is cyclically monotopic. Okay. So my theorem is, so let pi mu is cyclically monotone output plan and assume that mu is absolutely continuous with respect to the Lebesgue method. Okay. Then there exists a convex or semi-continuous function phi. Okay. I should also say proper, but anyway, proper means that it is not identical in. So a convex or semi-continuous function phi that phi is induced by the gradient of a convex function. So you see, there is no mention of any optimality. Okay? So all my statement is basically a cyclically monotone transport plan is induced by a map provided the initial measure is absolutely continuous. Okay. Alright. So I'm going to use this Rockefeller's theorem. In a anyway. So clearly my support is pi, right? So by Rockefeller, that by Rockefeller there exists a convex or continuous function p such that support of pi contained in the subdifferential of this guy pi. Okay, so this is by Rockefeller. So phi is convex. Okay, so it may take value infinity, right? Last time we mentioned that we are talking about convex functions, which may also take value infinity outside a convex domain. Okay, so let me define phi is all such x where it is finite. Of course, by definition of convexity, this is a convex domain. All right. So what we know about the boundary of that domain. So the boundary of this domain of phi. So this is at most n-1 dimension house topic. In the sense that you see that if you have a convex domain, okay, so let us take a point here. So you know that it has a supporting hyperplane. Now, in a small neighborhood, you see, this almost looks like a graph, right? So if I sort of zoom in here, so something like this one, right? Now, almost looks like a graph. So for every point here, you have projection onto this hyperplane, which is n-1 dimension, right? So basically, each neighborhood, for each point, you have a neighborhood where it almost looks like n-1 dimension, right? So from the picture, at least it is convincing. So the domain of phi is at most. I'll just say that it's greater than 0, right? Doesn't give past to such things. All right. Oh. Now, you remember that support is founded in the subdifferential. Okay, so and remember that definition of subdifferential is bigger equal px plus p times 1 minus x, right? So if this point is plus infinity, okay? If x plus infinity, I mean, it can never hold, right? So always the subdifferential is non-empty, provided x is in the domain of. In other words, if x does not belong to the domain, then this guy is infinity, and therefore the subdifferential must be empty. So phi basically doesn't give mass to the boundary of the domain. So basically phi gives all the mass to the interior of the domain of phi. Okay, so let me not write it. Okay. So now let us denote interior of domain of phi. So this is the interior of domain of phi. All right. So let us denote it by omega. Okay. So now let us compute mu of omega. Right. Mu of omega is basically my phi omega cross omega cross mu of omega. All right. So mu of omega is all right. Okay. So phi of domain of P cross Rn, it has full method, right? Because domain of P is empty. For domain of P is empty if not domain of P. Subdifferential is empty if domain of it does not belong to the domain of P, right? So this implies that mu of domain of P has full mass, right, by marginal condition, and mu is absolutely constant with respect to the level method. Okay? So the boundary doesn't give mass to such small sets. So this implies that mu of interior domain of P has full mass. Right? Mu is absolutely continuous. All right. Okay. Now, again, P is let us denote U set of all point X where P is differentiable. Now, in the interior of the domain of P, of course, this is a subset of the interior of the domain of P. Now, P is locally Lipschitz, right? So P is differentiable almost everywhere in the interior of domain of P. So this U has full mu method. Right? So see, so we are just bringing down to case by case, right? So we are just excluding all the bad sets. Now, here again, this is the point of differentiability. So of course, this is a Fourier set. And let us denote, and here you actually have here U is differentiable. So on U, gradient of phi exists on U. And therefore, if I restrict this map to U, this is a Borel. And my claim is that this map is my this map actually puts forward mu to it. Basically, so this map is defined only on U and mu almost everywhere. And my claim is that phi push forward. Okay, so whenever I'm writing this, that means this is defined almost everywhere, which from here you see it's defined only on the domain U. Okay. All right. So now let us prove this one. Okay. So let us denote S the set X gradient phi X, and this is defined only on Q, right? X. And let us look at the phi measure of S, right? So the phi of S, it has a full mass, right? So because so if you intersect this set S, right? So basically these are the points of differentiability of S, right? So S is basically U cross Rn. Now, so I included the whole Rn, right? And U is the point of differentiability. And but I have to include the derivative, right? Which is precisely the subdifferential of, right? So these are the point of. So now if I take the full pi of S, see pi of S, pi support of pi is included in the subdifferential. So this gives me pi of U cross Rn, and this is precisely mu of U, which is full mass. So this S, this set S has full pi measures. All right. Okay. Now I'm going to prove this. Okay. So it is enough to check on the sets of the top M crossing, right? So because these are the sets which generate the whole measure. So I'm going to check on these sets. They actually are. I mean, yeah, they are the same. Okay? And since pi has full measure, so I'm going to show that. So since pi has full measure, I can take intersection with S, right? So I'm going to show that this is. So I have to prove that this identity holds, right? And I'm going to prove that this identity holds on the sets of this form, right? And which is enough to check the sets of this form intersection S, right? Because pi has full, right? All right. So let me rewrite this set. S contains the point of differentiability of phi, right? So I have to take gradient phi inverse of n, right? And this also must come from n. Okay. So these are the first component. Okay, cross Rn, and I have to take intersection with this, right? You see, just I'm rewriting right? So this set, I have to take the intersection with S, right? So the second component must come from something of gradient, right? So I have to take the gradient inverse of N, right? And the first component must come from N. So they must come from both of these, right? And the second component is just, just the gradient of phi. So now you see, once you write this, you are done. So if I take pi, now pi has full measure, so I can just erase this S. This is pi. Again, S has full pi measure. I can just erase this S. Now this is Rn, right? So if I write a marginal condition, this is M intersection gradient P inverse of N, right? And which is precisely this identity, which is precisely identity. Let me write this way: mu of identity gradient phi inverse of N cross N. Okay? Let's just set equalities. So this proves that pi is given by a map. So in particular, if I choose m equals to Rn, if Rn, then this one is by marginal condition. This one will give me mu of n, which is equals to, from here. So I'm choosing m equals to Rn. So I mean, if you intersect any set with Rn in the set itself, right? So this is mu of gradient of n, and that is precisely the definition of gradient phi put forward mu of. So this proves that the optimal map is given by this one, and in particular, mu is the push forward. So this proves Brenier's theorem. So I haven't proved uniqueness for this map, which I'm not going to do because it will take some time. So the idea is, see, if I use duality, it is almost trivial. But if I don't use duality, the idea is that if you have two convex functions which be at a point, and suppose they are sub-differentials, they differ by some angle, then I mean, in order to reach, if you take any hyperplane here, if you lift sufficiently down, then it will also touch the lower hyperplane, right? So the subdifferential of this convex function is included in the subdifferential of this convex function. Okay, but but the other, when the opposite story doesn't go. Actually, what you can prove is that, I mean, in order to reach this direction to something like this direction, you need some time. Okay, so before that you cannot reach, and this has a positive distance, right? And for convex function, you have a somewhat implicit function theorem, which tells you that since the gradient doesn't vanish here, I mean, gradient of the difference between these two convex functions doesn't vanish here. So the points where they agree is at most h minus 1 dimension. Okay, so this is not smooth implicit function theorem, which holds for convex function, but not this function. Okay, so I don't want to go into that, but now, so this is what I wanted to tell about Brenier's theorem. Okay, so now let us come to the main topic, the regularity of the facts. Okay, so formally, by change of variable, let me just erase everything and let me set up my assumptions. Okay, so from now on, I will concentrate only on compact neighbors. Okay, so suppose that compact. All right, so let me fix. So again, cost is always today and tomorrow will be what it cost. Mu is absolutely continuous. Mu is also absolutely continuous. Okay. And for this term, I will assume that the support of mu is basically f here f. So let x and y, these are bounded, and this f vanishes on Rn minus x, vanishes on Rn minus y, and on this set x and y, there exists a constant c, such that on this set f is bound away from 0 and infinity. G is similarly, G is of space bounded away from 0 and infinity on y. So these are my whole set of answers. So last time we did a formal change of variable formula, and from now, so by Brenier's theorem, we know that at least we have a convex function which push forward mu to mu, and therefore by formal change of variable, you have determinant of V2 phi is x by g of gradient Px. So formally, not, I mean, in a classical sense, so this will be denoted by the Mond Ampere. All right. So from my definition, from our definition of assumption, so F and G are almost stays bounded away from below and infinity. So this almost behaves like a constant. Okay, so I'm denoting by what? Yeah. All right. All right. So this is one notion of solution, which I call Brenier solution. And there is another notion I'm going to define now for Alexander solution. This is as follows. Okay, so again, for a convex function, let us do a formal change of variable. Okay, so determinant of d2 phi, this is the Jacobian of the gradient phi, right? So if I denote by f, or yeah, if I denote by this f, right? So I change of variable. So this is precisely, let us say everything is smooth, right? X is equals to T1, right? So this is my the formal change of variable. Right? So here, if I do the change of variable, we get this one when everything is smooth, right? So now, of course, here I'm assuming phi is convex. So that, I mean, the Jacobian has a sign, and therefore it's now, of course, phi cannot be, may not be smooth. So here we are going to define. I mean, it has to be replaced by a little sub-difference. Right? So basically, this is the Lebesgue measure of sub-differential of f. Okay? All right. So given a convex function, okay, so the smooth case, the Lebesgue measure of the sub-differential of the set is given by this quantity, right? And I will say that this quantity, we will say that this is called the Mond Ampere measure. All right. So now it is, you can show that this is actually the whole measure and sigma finite. Okay. So I think let me yeah. So here so let me define or let me define definition. So we say that phi from a domain omega to r. Okay, I will explain in a moment what is my omega. We say that a convex function from phi from omega to r is a Alexander solution to the non-Ampere equation determinant d2 phi is equals to some not new. Let me say h. Okay, h if the non-Ampere measure. Look at this identity. So here this is determinant d2 phi is h, right? So basically integral h. So this holds for all is good. And so basically the Mond-Ampere I mean the existence and uniqueness of I don't have much time, so I'll just go directly to the business. Okay, so from here, okay, so according to my assumption, let us look at this one. So this tells you that the age here, the right hand side, my age is almost comparable to constant, right? So the Mond-Ampere measure in this case, if he is the Alexander solution, then this Mond-Ampere measure. So here, in my case, age is almost comparable to the constant. So this guy is comparable to the Lebesgue measure of age, right? So in case of Alexander solution, your Mond-Ampere measure is compared to the Lebesgue method of this set. Okay? All right. Okay, so Agnit will talk about the regularity of such equations, okay, and regularity of such solutions. So technically, under this assumption, what one can show is that phi is actually C0 alpha, C1 alpha, okay? And which relies on the strict convexity, which is the goal of this talk. Okay? So I will prove the strict convexity, and then Agnit will take over and he will prove the C1 alpha regularity of such solution. So the bottom line is a regularity theory. Yeah?
Previously, the Bernoulli solution when you prove the existence of P. You started with any convex solution.
Okay.
And show that it's a solution. Or like P, like you started with just anti-arbitrary P or because
Which one? Which one?
no, the previous
The previous Brenier solution. So it has three convex, no?
yeah, so any convex function.
No, so you have a major pi, and you have convex something pi, and the condition is that pi is supported on the
On the support
yeah,
of the P.
right. So I mean, this is half difference here for a convex function. So this is almost a graph, right? So you can think of it, it is C1 function. Right? So basically, graph of the gradient. Right? So pi is almost supported on a graph.
It should be on the support.
Right.
Then only like
Yeah.
P will.
Yeah. Okay. All right. Okay. So the bottom line is that such a solutions to such equations, a regularity theory exists. Okay. So if H is sufficiently regular enough, then your solution is also sufficiently regular enough. So here I didn't mention about what is my omega. So omega here, I mean, the first impression is that well, P is convex, omega must be convex. Okay. So here omega can be any arbitrary omega function. Okay. So here the definition of convexity is that P can be extended to a convex function in Rn. Okay, so this is my definition, right? So here omega not necessarily open convex, but P is just a restriction of a convex function with the domain. Okay. So what is for Alexander solution? I mean, you may such regularity theory exist for Brenier solution. You cannot actually expect any regularity at all, even for smooth densities. Okay, so here is the example. So this is V1. Okay, V1. So you are in R2. Your mu is just the Lebesgue method restricted to V1, and you want to transpose it to these two half walls. Okay, so mu is basically half of the Lebesgue method of P1 translated to minus 2e half Lebesgue method restricted to P1 translated to plus 2. Okay, so you just want the same half mass from here to here, half mass to here. Okay, so these are all the same size. Okay, from picture looks like it is bigger, but I mean this is basically this half translated to okay. So it is actually easy to see that if you send a mass just in a straight line, then this is actually optimal. Okay, so in fact we can give you a optimal map Tx from the equation. If you just if x lies on the positive side, then you just shift it to E1. Sorry, E1. Okay, this is and when if x lies on this side, then you just shift it to the left. Okay, and this map actually you can write it as a gradient of a convex function. 2 times mod x 1. So therefore, this must be optimal. So obviously, this map P is this is P. So this is a optimal map, and therefore P is a solution to Brenier solution. But you see, when T is T is not even continuous along this line, right? So even though the densities are regular, even smooth, so you cannot expect such regularity even for smooth densities. And you might think that okay, maybe this results from the disconnectedness of this set, but actually what actually showed that this is not the case. This continuity of the map doesn't come from the disconnectedness of the set. Okay, so he modified this example in the following manner. So I'll just explain it in a picture. Okay, so you just join a thin slit of epsilon. Okay? So this is of with epsilon, and in order to figure out the mass, you just modify this set so that this new set. This is my x, and this new set what we define after joining this slit is the y epsilon. Okay, so that y epsilon converges in some sense. All right. So now Caffarelli argued that okay, this if epsilon is small enough, then the optimal map cannot be continuous. Okay. So here is the heuristic argument. So this relies on something called what Caffarelli's argument was that see. So these are all induced by some potential field, right, which comes from the Kondratovich dual problem. Okay, and that potential actually converges uniformly to the potential of this problem. Okay, and therefore, by continuity of the Monge-Ampere method, we argued that towards the continuity of the Monge-Ampere, we argued that it has a singular part, right? So if you compute the Monge-Ampere measure of this function phi, okay, measure of this function. Okay, so let me fix the notation. Okay, so this I will denote by the mu phi of so the mu denotes the Monge-Ampere measure. So if you compute here, so what you will get. So this is just the x, right? So for x, you will get that's the Lebesgue measure, but it also has a singular part. Okay, so it also has a singular part. So that will give you 2 times. So it will be 4 times the h1 measure restricted to this by h1 is equals to 0. So 0 is equals to x1 is equals to 1. Okay. You see, it has a singular part. So the Caffarelli's Caffarelli use that in the convergence of the potential, uniform convergence of the potential to the contour. But here is another argument which shows that optimal maps cannot be continuous. Okay, so it relies on something called the stability of the map. Okay, so let me denote that P epsilon is the optimal map from x to y epsilon. You know what I mean. Okay, so in y epsilon, and claim is that, and all right. Okay, so yeah, all right. So it denotes this depends on the stability of the map. So here is what it says. So your mu is fixed, okay, and you have the sequence of measures mu k, which converges weakly to nu. Okay, and let t be the optimal map from mu to nu, and let us denote pk the optimal map from mu to nu k. Assume that this map is unique. Okay. Then your pk converges to t in mu measure. Okay. So basically, so it converges to mu in mu measure. So So what is that means is that suppose if you take a chunk of mass here, okay, then as Tk converges to T, and so your original map just shifting this mass to here, right? So it Tk converges to T mu measure, meaning that for K large enough, this mass, a significant portion of you cannot have two less mass each. Okay. All right. So using that, let us show that the optimal map cannot be continuous if it is sufficiently small. So for the moment, on the contrary, assume that T epsilon is indeed continuous. Okay. So let us take a point here. Okay. Again, so this will T epsilon will map to some point here. Okay. By again stability of the map. Okay. So this is your T epsilon. Now, if you take a point on the right, this will also point to somewhere here. Now, let me join this straight line. Okay? Now, if T epsilon is continuous, then the image of this line should also be connected, right? So, and the only way to go is to go through this tunnel. Right? So, at least you will find a point here which has pre-image somewhere here. So let me erase everything and just keep that point. So just to mention that you have a point which has somewhat large downward rays. Okay, so let me denote this point x1 and this is T epsilon x1. Okay. Now again, if you take a point somewhere here, then again by convergence method, it has to map almost horizontally to some point here. Let me denote x2 and this is T epsilon x2. Okay, so now let us look at the image, the directions. Okay, so x1 to x2, something like this, and here x1 to x2, something like this. Right? So which looks like more than 90 degrees, at least from the picture. Okay, so this actually cannot happen. So that is I by 2, and that would contradict. So last time I mentioned that contradicts the cyclically monotone property of optimal map, or in other words, so if you want to direct compute it, what we have is the angle T epsilon x1 minus T epsilon x2 of x1 minus x2 is strictly less than 0, and sorry. So if you do some algebra in this, then this will give you T epsilon x1 minus x1 squared plus T epsilon x2 minus x2 squared is strictly bigger than epsilon x1 minus x2 squared plus epsilon x2 minus x1 squared. Okay, so just from this inequality, you do some algebra, you get this inequality that contradicts the optimality, right? So you're sending the point x1 to a point which costs more than you do it otherwise. Okay, so that proves that it is the optimal map is discontinuous. Okay, so Caffarelli understood that. So only only connecting assumption would work, that you require some convexity assumption, and that is a non-trivial result is convex analysis that I will mention now, which I think what inspires Caffarelli to consider the convex support. Okay, so the result is as follows. So see, by definition, the subdifferential of a subdifferential of a convex function. This is a convex closed set. Okay. So if you want to compute subdifferential, assume that x is an interior point, interior of the domain of P. Then the subdifferential at x you can compute by taking all the limits xk converge to x. Okay, xk of course belongs to the domain. Let me denote it by omega. And suppose xk is a point of differentiability which exists for almost every point, right? So you are taking xk differentiability point and you are considering a sequence xk of differentiability points which converge to x, and you are considering the gradients. Of course, this limit is in the subdifferential, follows from the definition of subdifferential. Okay. Now, if there is the convex, so since this is convex, okay, so convex hull of all such limits also belongs to the subdifferential, and subdifferential is the closed set. So you have to take the closure. Okay. So this is basically it. I mean, so this inequality is of course obvious, and you have actually this inequality. So I will give why it should be true perhaps later, but for the moment, I mean, I'm just going to skip the proof or some intuition of the proof, but let us just assume it and let us proceed. Okay. All right. Okay. So yeah. So all right. Okay. So let us see what happens to the to our Brenier solution. So what we have now is that if P is an Alexander solution, then the Monge-Ampere measure is almost comparable to the Debabrata, right? That is what we have. Now let us see what happens to the Brenier. Okay. So again, I need a little bit result of on a convex analysis. So let us look at now the Brenier solution. Gradient P equals forward mu is equal to nu. Then I have this density, everything. Okay. So my claim is that if I compute, so mu is a point of differentiability of and let us take gradient P of P. Okay. Of course, this is lies inside the support of mu. Okay. If I take the closure, actually this is equal. Okay, so let me just write very clearly. So support of P on the differentiable points contained in the support of mu, and if you take the closure, it is actually equal. So basically, what it says that every point of differentiability and the image is inside the support of mu. All right. Okay, so yeah. So this follows from, so let us take a point x inside U and let us denote y equals to gradient P of x. Okay. Now here is another property of the subdifferential or convex function. If a convex function is differentiable everywhere, then it is C1. Okay. So you don't even need to prove the continuity of the derivative, which results in something called the outer semi-continuity of the subdifferential. Okay. So given a point x, for every epsilon, okay, for epsilon positive, there exists a delta such that if you compute the subdifferential of P around this point, it cannot too deviate from the subdifferential at the point x, and which I'm assuming is point of differentiation. Okay, so subdifferential around in neighborhood cannot deviate too much. Okay, so if I take the new method, so then it will be less or equal. Okay. Now this guy, by definition, mu of gradient P inverse of subdifferential of and therefore these are all the sub-differentiable CL, and we are considering all such points where it is actually differentiable. Right? So this is basically mu of B delta intersection the point of differentiability. Right? And mu of this one is bigger equal to this one. Right? So if x is in the support of mu, then this guy is always positive for every delta, right? And which in turn gives that this guy is positive for every epsilon. So this identity is trivial. Okay? For the other one, it is also, I mean, try to read just 1 or 2 lines using the definition of sum. Okay? So this identity holds. Okay? And another thing which I need is the following, that the integral over d mu, or so mu of say e, which is equals to, so here mu is our gradient phi whose forward mu, okay, and see mu and nu, they almost satisfy the same hypothesis, right? So interchangeably, and therefore the same argument tells you that your mu is actually inverse of you take the inverse gradient phi inverse mu, and this is the gradient of subdifferential whose forward mu. So if you compute the measure mu, then what you will get, so this is gradient phi star whose forward of mu, which is precisely mu of this inverse, gradient phi star inverse of E, and this is precisely mu of this quantity is gradient phi star inverse, right? So this is technically gradient phi, which you will have is the subdifferential of phi. Okay, so this is what we derived for Brenier solution. Now let us okay. All right. All right. So this is what I. No, this is not mu. This is mu, right? So mu. So that is what I. Okay. Okay. So let us write down this identity according to our assumption that mu and mu are actually continuous. Integral over E, mu has density F, which is equals to integral over mu. Integral over subdifferential T or E, it has density G. Okay? Now, let us look at this one. Integral F is bounded below and above by a positive constant, right? So this almost behaves like measure of E. Okay? And here we have G, right? And which has a support, right, inside Y. So this integral is actually integral over Y. And now on this set, G behaves like almost like a constant. So this is almost differential phi of P intersection Y. Alright. So for the Brenier solution, what you get, according to our assumption, that you don't have a full control on the Monge measure, right? You only have to see the portion which is inside this one. Right? So if you look at this example, what happens is that if you compute the Monge measure around this point, on this line, what you will get is full rectangle. Okay? So basically, this set is just one dimensional, which has level measure 0. But the Monge measure, it doesn't have level measure 0 because it is the full rectangle, right? But if you take the intersection with Y, now it is so that is the main problem, and this can be resolved by just the consideration what we have here. Okay, so let me what Caffarelli need is the following. Okay, so let me write down the theorem which was Caffarelli proved, and then we proceed. Okay. All right. Also, theorem 1992. Ready? Okay. So assume these are all my assumptions. Okay, assume A holds. A holds and P is a Brenier solution. Okay, this is a Brenier solution. Further, assume that Y is convex. Then P is a Alexander solution. Okay, so this is one part, and the most important part is that P is strictly convex inside. And this is where I will stop and Abhi will take over. Okay. Okay, so this is the theorem I'm going to go, and I'm going to keep this line for the rest of the talk, which is almost over. Okay, so I'm going to divide the proof into several parts. Okay. Step one. First, you remember that our potential. So this is given by the suprema. So phi is convex, right? So phi of z is the suprema of phi of x plus p minus x, where x is inside x and p is in the subdifferential phi of x. Right? So this is obvious because phi is convex. This is at each. So I mean, of course, the graph always lie above this one, and for each point x, you have the equality. For each point z inside x, a hyperplane will exist. Okay, so now look at this definition. My x is bounded, right? And therefore, this definition makes sense even if z is outside x. Okay, so I'm going to set phi hat, okay? And this makes sense for all. So here, all right. So in the first step, what we're trying to do is that, of course, you see, at least we have some information according to my linear solution. We have some information on the Monjamper. Okay. So first, we are going to show that this is actually, if y is convex, then this equality holds, right? So therefore, we have the full control of the Monjamper measure, and therefore this is Alexander solution. But we don't know what happens at the boundary, right? So all we know is that the gradient, everything lies inside it. So the boundary point is we don't have any control. So this is the first step. We just extend it and try to see what happens outside the set y. Okay? So the first observation is that, of course, phi hat is equals to phi in x. Right? And because of that, if you take an interior point, okay, at least locally, every subdifferential of phi is a subdifferential of phi hat and vice versa. And phi hat, you see, phi hat is, yeah, phi hat is all, the same, right? And above that, we don't know anything, right? It could be something like this. So we have just extended. Yes? So if I take a point x0 inside, at least as long as we stays inside x, this hyperplane restricted to this length will lie below the extended function. So basically, at least locally, this is a supporting hyperplane, but phi hat is convex. So and local property is global property. So the subdifferential of phi hat is equal to subdifferential of phi in x. Okay? So at least inside x, we know what happens, and now let us look at what happens at the bounded. Right? Now we know that the subdifferential phi hat, which is the same as subdifferential phi of x at the differentiability points. Okay, so this lies inside y. Right? And now subdifferential phi every point x, phi hat every point x, if you compute this one, now you use that one. Okay, so that it is basically the closure of the convex hull of this one, and everything lies outside, inside the domain y, right? So because this identity, because of this identity, every point of differentiability lies inside y, and y is convex. So this is contained in y closure, right? And boundary of y closure has measure 0. So the level measure of y closure minus subdifferential phi hat of x, this has level measure 0. Okay, so at least this gives you some of the control on the applied measure, right? All right, so this tells you that at least phi is an Alexander solution to phi. Now we have to see what happens at outside y. Okay, so for step 2, the thing is that the subdifferential phi hat of Ra is actually y closure. Okay? And this is what we are going to do. We are going to extend the definition. Okay, so here x is okay. So how much time I have? 5 minutes or so. So what I will do, I will then prove that it is a Alexander solution. So the alternative, perhaps I will do it tomorrow. Okay, it's better. Otherwise, it will be too much. So I'll just compute what. So I'll prove what equation it satisfies current, the 4 alternatives, and perhaps I will do 2 alternatives and 2 alternatives tomorrow. Is it okay?
Maybe all 4 alternatives in one day is better. No? People can follow better.
Yeah. Then 5, 15 minutes, 20 minutes tomorrow. All right. Okay, so let us try to compute this. Let us try to find out what happens outside R. Okay. All right. So from here, you see, subdifferential phi hat x is contained in y bar. Okay. Now, I'm going to take a closure. Okay, the closure is also inside y bar. Okay. Now, which I will denote. The closure is basically usually this is contained inside this one. Okay, so but I will let me keep this as closure. Okay? So let's keep this as closure. All right. So this closure is already inside y bar. Now you also see that I also mentioned I think erased. So y closure is basically if you take subdifferential phi of u, gradient phi of u closure, right? So this guy is contained in the gradient phi of u, which is same as gradient phi at closure, right? Now you see here you have a, here you have y, right? So and without the closure, this set is smaller, right? So if you take the closure, the equality persists. So basically, this is equals to this one, right? Okay. And we have also this one. All right. So now let us try to see what is the equation satisfied by phi hat over R. Okay. So once we check the closure, so let me modify my definition of phi hat. Okay. So remember that y is bounded, right? And y is bounded, and the subdifferentials are contained in the y, right? So here these p are actually contained in y is contained in say p0r. Then all this p, then this p belongs to a fixed form, and therefore each of these functions is Lipschitz, right? As a function of the Lipschitz constant is precisely r. So this phi hat is actually continuous. So first in this definition, what I'm going to do, I'm going to replace this phi by phi hat. It doesn't change, it's continuous. And then I can just take the closure, right? Because it is continuous for current, so this definition doesn't matter. Now by doing that, what we achieve is that get the supremum for each z, a supremum is attained. All right. Now once we have that, I'm going to show that the this inequality. Okay. So as a first step, I'm going to show that at the set of all differentiability points of phi hat, this is inside y closure. Okay. So if I show that, then almost we are done. Okay. So if let us take a point, say not differential differentiability points. All right. Yeah, this is fine. So let us take we have a differentiability point of theta. Okay. Now from my definition, hat of z, this identity z hat, this holds from my definition of z hat, I have at least there exists a x hat, and x hat is in x part, p hat is in the subdifference P of x hat, such that the equality is attained. P hat of c hat is equal to p hat of x hat plus hat of p hat minus. All right. Now what I know is that the graph p hat of y lies above p hat of x hat plus p hat times p hat minus x hat. So this is right. Yeah. So p hat is in x hat, right? All right. Okay. Yeah. So this is true for every y, right? Now from this, if I replace this once, sorry, y minus, that is y minus x hat. Okay, so if I replace my p hat by from this equation, so what we get is that p hat of p hat and plus p hat of so y minus p hat minus x hat. It will be minus, right? I'm replacing p hat y minus x hat, right? Yeah. Thank you. Yeah. Yeah. So this tells you that the subdifferential p hat belongs to subdifferential p hat of z hat. Now this is the differentiability point, right? So this is actually equals to then gradient of p hat of z hat. So you see, we took any arbitrary differentiability point of z hat, okay, and we saw that there exists a p hat which is inside this x bar, while it is equal, right? So outside it doesn't have any mass. Okay. So let me just stop here by saying that. So as a result, what we prove is that the subdifferential phi hat of subdifferential phi hat of Rn is equals to y closure. Okay. Now you see subdifferential phi hat of x part is already y bar, right? So subdifferential of phi hat, it has almost full level method, right? Subdifferential has almost full level method. So this guy is at least say some y1. Let me denote this by y1, and then Lebesgue method of y closer minus y1 is it has 0 Lebesgue method, right? So if I want to compute the subdifferential p hat of so Rn minus x. Okay, so if I want to compute this one, then this guy is precisely subdifferential phi hat of Rn minus x. I will take intersection with subdifferential phi hat of x. Okay. So this is and union this y minus y closer. Okay. Y minus y closer minus 1. Right? And so the whole the remaining portion, so of course here I proved that the subdifferential of phi hat is called Ra, right? So now if I want to compute the Monge-Ampere method outside x, so we are just taking the intersection with x and the remaining portion. So this is y1 and this is the remaining portion. The whole portion is y. Now you see that this has Lebesgue method 0 and this has Lebesgue method 0. Again, result in convex analysis, which tells you that see if P is in differential of intersection of the subdifferential of 2 points. Okay? Then this implies P is in the subdifferential of P, that is X is in the subdifferential of P star of P. Similarly, V is in the subdifferential P star of P. So these 2 points belongs to the subdifferential of Phi star of P. So that means P is not a differentiability points of Phi star, and such a points have Lebesgue method 0. Okay, so this quantity has Lebesgue method 0. So ln of subdifferential Phi hat of Rn minus x Lebesgue method 0. So if I combine these two, what we prove is that it satisfies the Monge-Ampere equation in the following. Okay, so Monge-Ampere method of the subdifferential phi hat is some h, where h is bounded below by some constant on x and bounded above by constant on x. Okay, and it vanishes outside x. Okay, so this h basically, I mean, this meaning h is almost equals to a constant in x and 0 in Rn minus x. Okay. And so this allows us to at least, I mean, apply this alternative, which I'm going to discuss tomorrow. Okay, so if phi hat is not strict on this, then we have some alternatives, and we'll exclude each one by one. Okay, so I'll start from here.